that everything we perceive as our reality, the vastness of space, the pull of gravity, even the relentless march of time, wasn't fundamental in itself.
Right.
Instead, what if it was all just a projection, like a cosmic hologram, emerging from a much flatter, simpler dimension?
Sounds like something straight out of a blockbuster sci-fi movie, doesn't it?
Exactly. But for theoretical physicists, this isn't just some whimsical thought experiment. It's a groundbreaking, rigorously mathematical idea known as the anti-de Sitter conformal field theory, or AdS CFT correspondence.
And what's truly fascinating here, I think, beyond the initial mind-bending concept, is that this isn't just philosophical musing or some loose analogy.
It's precise.
It's a precise mathematical conjecture that suggests an exact equivalence between two radically different physical theories. So on one side, you've got a world with gravity and extra dimensions.
The familiar, sort of.
Well, familiar in a theoretical sense, yeah. And on the other side, a world without gravity, existing only on its boundary. This correspondence, it offers us a profound shortcut, almost like a Rosetta Stone, for understanding the very fabric of existence. It pushes us to fundamentally rethink what reality truly is at its most basic level.
And that's exactly our mission for this deep dive today. We're going to journey through this revolutionary idea, starting from its, surprising and elegant foundations. We'll then explore how it's being wielded as a powerful tool to solve some of the toughest problems in physics. Think exotic matter in the early universe, the mysteries of black holes.
Really fundamental stuff.
Totally. And finally, we'll grapple with what it truly means for our understanding of reality and what it suggests about the universe you inhabit. Prepare to have your perspective shifted, maybe just a little bit. Okay, so at its very core, the AdS CFT correspondence is built upon this profound duality, a conjectured, almost magical equivalence between two descriptions of reality that, on the surface, seem utterly disparate.
They really do.
This radical idea was first proposed by the brilliant physicist Juan Maldacena back in 1997. So on one side of this duality, you have a theory of quantum gravity operating within a higher dimensional spacetime, specifically what we call a D+1 dimensional anti-de Sitter, or AdS, spacetime.
Right, the gravity side.
And on the other side, quite unexpectedly, you find a non-gravitational quantum field theory, known as a conformal field theory, or CFT, which lives on the E-dimensional boundary of that higher dimensional space.
Yeah.
As Maldacena put it so well, the fundamental idea is that a theory without gravity on the boundary is equal to a theory with gravity in the interior. Simple statement. Profound implications.
It's a bit like a sophisticated cosmic hologram, isn't it? Think of an old credit card with that 2D holographic sticker that, when you tilt it, reveals a full 3D image.
Right. I remember those.
In a similar vein, the conformal field theory, living on that lower dimensional boundary, acts as a hologram. It encodes all the information about the gravitational theory unfolding in the higher dimensional bulk or interior.
But it's not just an analogy, right? That's key.
Absolute crucial point. It's not merely an approximation or a loose analogy. It's a conjectured exact equivalence, meticulously detailed with a kind of dictionary that allows physicists to translate concepts, calculations, everything between these two seemingly alien worlds.
Wow.
This duality, it profoundly challenges our deepest intuitions. It suggests that gravity, maybe even the geometry of space-time itself, they might not be fundamental entities. They could be emergent phenomena arising from a simpler non-gravitational system on some distant boundary.
And here's where this duality isn't just elegant, it's incredibly powerful and, useful. It has this feature called strong-weak duality.
That's a powerhouse.
Yeah. This means that when the boundary CFT is strongly coupled, so its particles interact so intensely that calculations become just nightmarishly complex, virtually impossible with traditional methods.
Perturbation theory just breaks down completely.
Exactly. But then the corresponding gravitational theory in the bulk is, conversely, weakly coupled. And in that weak coupling regime, the, mind-boggling quantum gravitational stuff can be approximated by something much simpler. Classical Einstein's general relativity.
Something we actually know how to calculate with.
Right. Suddenly those previously intractable problems on the strongly coupled side become solvable on the weakly coupled gravity side. Right. So this empowers physicists to translate seemingly impossible problems into manageable ones. It opens up entirely new avenues for understanding exotic matter, like the Quark-Gluon plasma, which we'll definitely get into.
It's like finding a secret back door into a locked room.
Yeah, totally. And this remarkable property is precisely what makes AdS CFT the most successful and precise mathematical realization of the holographic principle.
Ah, right, from Hooft and Susskind. Exactly. That abstract idea was first proposed by Gerard Hooft and later significantly developed by Leonard Susskind. They were inspired by the peculiar thermodynamics of black holes. Remember how the entropy, the information content of a black hole, turned out to be proportional to the area of its event horizon?
Yeah, not the volume, which blew everyone's mind.
Right, not its volume. This was a radical suggestion. It implied that all the information contained within a 3D volume could somehow be encoded on a 2D surface. But before Maldacena's work, it was a profound but, abstract concept.
Hard to get a handle on.
Very. AdS CFT provided the first concrete, calculable framework for this abstract idea. It let us quantify and explore this utterly radical perspective on information in a gravitational universe. It really gave the holographic principle teeth.
Okay, so let's zoom in and set the stage for the gravitational side of this correspondence. This higher dimensional reality, the gravitational stage, lives in what's known as anti-de Sitter space.
AdS.
Now, our own universe, on cosmic scales, we generally think it's flat or maybe even positively curved, expanding outwards. But anti-de Sitter space is fundamentally different. It has a constant negative scalar curvature.
The opposite sign.
Exactly. To visualize this, don't think of a flat sheet or the surface of a sphere. Instead, imagine something like a Pringle chip or the surface of a saddle.
That saddle analogy is pretty good.
Yeah, if you walk along one direction, you curve upwards, in another you curve downwards. Anti-de Sitter space has this kind of inward-bending, hyperbolic curvature everywhere. It constantly pulls things back in, unlike our universe, which tends to push them apart.
And to help visualize this, especially for a, say, D+1 dimensional anti-de Sitter space, we often use what's called the solid cylinder model.
Okay.
Picture a cylinder extending infinitely upwards and downwards that represents the flow of time. Each horizontal slice of this cylinder is a 2D hyperbolic disk, like a cross-section of that saddle shape. Now, what's truly unique and central to AdS is how distances behave. They become increasingly stretched as you approach the edge of this disk, the boundary.
Stretched. How so?
Well, if you were an observer inside this anti-de Sitter universe and you tried to move from its center towards that boundary, you would literally appear to shrink and slow down to an outside observer.
Whoa.
And from your own perspective, your own clock, you would never actually reach the edge in a finite amount of time. The boundary is an infinite distance away in terms of the internal AdS metric. It's a universe that, despite having a boundary, is endlessly deep in a sense.
And this outer surface of the cylinder, this infinitely distant edge, that's absolutely crucial, isn't it?
Absolutely. It's what we call the conformal boundary.
Right.
It's a D1 dimensional sphere of space extended through time, mathematically RSD1, and it's precisely on this boundary that the dual conformal field theory resides.
The hologram lives there.
The hologram lives there. And what's truly fascinating is that even though the boundary is infinitely far away geometrically, light rays within AdS can actually travel to this boundary and reflect back to the center in a finite amount of time.
Okay, that's counterintuitive.
It is. But this continuous interaction, this back and forth between the bulk and its boundary, is absolutely essential for the dictionary of the correspondence to function. It enables that constant interplay of information.
So the choice of AdS wasn't just random, though.
Oh, far from arbitrary. It's a deep mathematical necessity, rigorously dictated by symmetry. The group of isometries, these are the transformations that preserve distances and angles within the D+1 dimensional AdS space, mathematically SOD2. This group exactly matches the conformal symmetry group of a D-dimensional conformal field theory.
The symmetries line up perfectly.
Perfectly. For those less familiar with the notation, these symmetry groups essentially describe all the ways you can transform the space or theory while keeping its fundamental properties intact. This perfect one-to-one match between the symmetries of the bulk gravity theory and the boundary quantum field theory isn't just a coincidence. It's the foundational pillar upon which the entire AdS CFT correspondence is built.
Wow.
It's a profound hint that the geometry of the bulk is exquisitely tailored to the symmetries of its holographic dual.
Okay, so we've laid out the gravitational stage in anti-de Sitter space. But what about the other half of this cosmic equation, the quantum hologram that lives on its edge? Let's shift focus to the conformal field theory itself.
The CFT side, yeah.
A CFT is a very special, highly symmetric type of quantum field theory defined by its invariance under conformal transformations.
Right.
These are transformations that preserve angles, but crucially, they allow for the rescaling of distances. So in addition to the usual translations and rotations, CFTs are also invariant, under dilation, stretching or shrinking everything uniformly, and something called special conformal transformations.
And the implication of this scale invariance especially is incredibly profound.
How so?
It means the theory possesses no intrinsic length or mass scale. So its physics looks identical no matter what magnification you choose to view it at. It's scale-free.
Like fractals almost.
In a sense, yeah. This is why conformal field theories are often used to describe systems right at the critical points of phase transitions. Think of, say, the liquid-vapor critical point of water. At that precise temperature and pressure, there's no distinction between liquid and gas. The system's long-distance behavior becomes scale invariant, exhibiting no preferred size. CFTs nail that description.
And there's a key tool for understanding them, right? The OPE.
Yes, the operator product expansion, or OPE. It's a cornerstone principle. It basically states that the product of any two local operators at nearby points in the theory can be expressed as an infinite series of single local operators at just one of those points.
Okay.
The beauty here is that conformal symmetry places extremely tight, almost unforgiving constraints on how these expansions work.
Yeah.
It tells you a lot about the theory just from the symmetry.
Which leads to the bootstrap idea.
Exactly.
Right.
That concept of OPE naturally leads to a powerful technique called the conformal bootstrap. The requirement that this operator product expansion must be associative, meaning it gives the same result no matter how you group the operations, provides an incredibly potent self-consistency condition.
So the theory has to hang together perfectly.
It has to. This bootstrap approach lets physicists place very strong constraints on the allowed dimensions of operators and their coefficients within the theory. In some remarkable cases, it even allows a CFT to be solved entirely, giving a complete description of its dynamics without ever needing to write down a specific Lagrangian, which is, the traditional starting point.
That's amazing. All right, so we have anti-de Sitter space with its unique curvature and a conformal field theory on its boundary governed by these powerful symmetries. But what does this all mean for that extra dimension in AdS? If the boundary is flatter, but somehow encodes the higher dimension, what is that extra dimension if not just another spatial direction? That feels like a crucial piece of the puzzle.
That's an excellent question, and it's maybe one of the most elegant and profound parts of the entire correspondence.
Okay.
The extra dimension in the anti-de Sitter bulk is not a conventional run-of-the-mill spatial dimension like up, down, left, or right. Instead, get this. It serves as a geometric representation of the energy scale of the conformal field theory.
Wait, the dimension is energy scale.
It means that motion along the radial coordinate of AdS moving from the boundary deeper into the interior directly corresponds to flowing from high energies, the UV or ultraviolet regime, down to low energies, the IR or infrared regime, within the conformal field theory.
So going deeper into AdS is like zooming out in the field theory.
Precisely. This remarkable connection essentially geometrizes the process of renormalization, one of the deepest and most complex concepts in quantum field theory. It gives a concrete spatial interpretation of how a theory's behavior changes with energy scale. It's like the universe is folding its energy scales into geometry.
Wow. Okay. This whole mind-bending idea, the Maldacena conjecture, it didn't just materialize out of thin air, did it? There was a buildup.
Oh, absolutely. It was really a brilliant synthesis of decades of prior research.
Right.
You had string theory initially trying to describe the strong nuclear force inside hadrons, then evolving into a candidate theory for quantum gravity. Then came Hitt's groundbreaking work in the 70s, hinting that in a certain limit, gauge theories, the quantum field theories describing fundamental forces, could actually look a lot like string theories.
The large N limit.
The large N limit, exactly. And of course, there was the notorious black hole information paradox. Bekenstein and Hawking's work suggested black holes might destroy information, seemingly violating quantum mechanics. All these diverse threads, these deep insights, eventually converged and paved the way for the holographic principle itself.
And Maldacena tied it all together.
Precisely. His seminal 1997 paper brought all these disparate elements together through what's called a D-brane construction.
Okay, D-branes. Remind us.
Right. D-branes are these extended, sort of membrane-like objects that exist in string theory. They act like surfaces where open strings can end. Maldacena considered a stack of ND3 branes in type IIB string theory, and what he found was astonishing.
This system yielded two completely equivalent descriptions.
Two ways of looking at the same thing. Exactly. From one perspective, the low-energy dynamics of the open strings attached to these D-branes are described precisely by a 40-gauge theory specifically, the highly symmetric N4 super Yang-Mills theory.
Okay, that's the field theory side.
That's the field theory side. From the other perspective, these D-branes themselves are massive objects. They warp spacetime, creating a gravitational field described by closed strings. The profound insight was that in a specific low energy limit, these two seemingly different descriptions become completely equivalent, revealing a deep underlying unity.
So the archetypal example, the one everyone studies, is this duality between type IIB superstring theory on that specific space, AdS OSA,
Anti-de Sitter space in 5 dimensions times a 5-dimensional sphere, yeah.
and the N-4 super Yang-Mills theory in 4D Minkowski space. Now, these are often called toy models, right? Because they're not exactly our universe.
Correct. They're not precisely our messy, non-supersymmetric universe. However, their incredibly high degree of symmetry makes them mathematically tractable. It allows physicists to perform incredibly precise tests of the duality and really build out that crucial dictionary.
The translation guide.
The translation guide, exactly. And this equivalence is made wonderfully explicit through that bulk boundary dictionary we mentioned. It establishes an exact point-for-point mapping of physical quantities.
Give us some examples.
Okay, so a bulk field, let's call it X, existing in the AdS interior corresponds to a local operator, OX, in the CFT on the boundary. The mass m of that bulk field maps precisely to the conformal dimension of its corresponding boundary operator.
Okay.
A black hole within AdS is dual to a thermal state, like a plasma, within the CFT, and their temperatures are identical. Even more fundamentally, a single fundamental string that stretches from the bulk and ends on the boundary is dual to a quark in the gauge theory. And a complex thing like a Wilson loop in the gauge theory corresponds to calculating the quark-antiquark potential using strings in the gravitational theory. It's truly a two-way translation guide for the universe.
And this is where that strong-weak duality we talked about becomes an indispensable superpower.
Right, absolutely. The classical supergravity approximation on the gravity side, which is far easier to work with, is valid when the 'Tent-Hooft coupling, Tull, and the number of colors, n, are both very large on the gauge theory side.
Okay.
What's critical is that this is precisely the regime where the gauge theory itself is strongly coupled, and traditional perturbative methods, the bread and butter of quantum field theory, are completely useless there.
So it's like a cheat code.
It really is. The correspondence doesn't just offer an alternative. It provides a pathway to understanding phenomena that were previously entirely opaque to us. It really flips our approach on its head. For years, physicists were hitting a wall with strongly coupled systems, and then Maldacena essentially handed us a crowbar.
Okay, now let's move beyond the elegance of the framework and see how this mind-bending theory is actually being deployed to tackle real-world puzzles, starting with the really extreme conditions found in the early moments of our universe.
Right. One of the most impactful applications has definitely been to the Quark-Gluon plasma, or QGP.
That ultra-hot soup after the Big Bang.
Exactly. An exotic state of matter, this ultra-hot, ultra-dense soup of quarks and gluons that we believe existed just microseconds after the Big Bang. And we can fleetingly recreate this QGP in heavy ion colliders like RHIC at Brookhaven and the LHC at CERN.
But it's hard to study.
Incredibly hard. The key challenge is that this QGP behaves as a strongly coupled fluid. This makes it incredibly difficult to analyze with conventional methods based on weakly interacting particles.
And that's where AdS CFT comes in.
That's where it shines. Remember the dictionary? A black hole in the AdS bulk is dual to a finite temperature CFT plasma on the boundary. This allows us to study the complex, real-time dynamics of this strongly coupled turbulent plasma by analyzing the simpler physics of classical fields evolving around a black hole in the bulk.
Okay, and this led to a big prediction, didn't it, about viscosity?
It did. A landmark result that truly stunned the physics community. Holographic calculations, using this black hole analogy, yielded a ratio of shear viscosity to entropy density E's that was universally equal to 1/4.
1/4 pi. Just a number.
Just a fundamental number. Now, this is a remarkably small value, much, much lower than for any conventional fluid we know, like water or honey.
And the experiments.
The truly astonishing part, the part that connected theory to experiment, was when experimental data from RHIC indicated that the real-world Quark-Gluon plasma has an ACE ratio very, very close to this holographic prediction.
Wow.
It suggested that the QGP is an almost perfect fluid, flowing with extremely low internal friction. This was a property that was incredibly challenging to predict otherwise. So yes, this theoretical model, inspired by black holes in a different dimension, predicted the behavior of matter created in our most powerful colliders with incredible accuracy. That's truly mind-blowing.
It really is.
It absolutely was. A massive validation, a moment where theory and experiment converged beautifully, though it's crucial to add a note of caution.
Ah, okay. It's not perfect.
The picture isn't always perfectly complete. For instance, when attempting to model phenomena like jet quenching, that's how high-energy quarks lose energy as they blast through the QGP. The holographic predictions, while still insightful, showed some disagreement with later, more precise LHC data.
So what does that mean?
It highlights that while N4 Super Yang-Mills is an incredibly powerful toy model, it doesn't capture all the intricate complexities of quantum chromodynamics, QCD, the true theory of the strong force, like its running coupling constant, which changes with energy. So AdS CFT is a powerful tool, but understanding its specific limitations is just as vital as celebrating its spectacular successes. It's a lens, not a perfect mirror.
Got it. A powerful but imperfect tool. Okay, so beyond the fiery crucible of the early universe, this holographic principle has found fertile ground in areas far removed from cosmology. You mentioned condensed matter theory, AdS CMT.
Exactly, condensed matter theory. Here, holography is being used to investigate strongly correlated electron systems. These are materials, things like high-temperature superconductors or so-called strange metals, where the complex interactions between electrons make conventional quantum field theory methods utterly fail.
Another area where things get too complicated.
Precisely. It's another domain where the interactions are so strong that standard approximations break down, and AdS CFT offers a unique path through.
Like holographic superconductors.
Exactly. For example, physicists have been able to construct holographic superconductors. By introducing a charged scalar field into the anti-de Sitter bulk, they can create solvable models where a dual superconductor spontaneously emerges on the boundary below a critical temperature. We can actually watch superconductivity turn on in the model.
And strange metals. Those sound weird.
They are weird. These are materials exhibiting anomalous transport properties, like electrical resistivity that scales linearly with temperature, which defies standard explanations based on particle-like quasi-particles. Studying charged black holes in AdS provides insights into these perplexing materials and their strange behavior.
So it's not just modeling things we already know.
Oh no, it's proving to be a tree discovery engine. It's uncovering novel phenomena and transport coefficients that were first predicted holographically, and then in some cases later derived more generally within field theory itself. It's a fresh perspective that's breaking theoretical impasses.
But perhaps the most profound insights offered by AdS CFT are directed at quantum gravity itself, right? Yeah. Especially regarding that infamous black hole information paradox we touched upon earlier.
Yes, the Correspondence offers a very elegant, albeit still conjectural, resolution to this paradox.
How so?
Well, remember, the boundary CFT is, by definition, a unitary quantum system. Information is always conserved within it. And because this CFT is supposed to be an exact dual description of the bulk,
Then the bulk must be unitary too.
logically it follows that the black hole evolution in the bulk must also be unitary. Information cannot truly be lost if the boundary description conserves it. But beyond this, perhaps the most revolutionary insight to emerge is the Ryu-Takayanagi, or RT formula.
Okay, RT formula, what's that?
This provides a direct quantitative link between entanglement, a cornerstone concept of quantum mechanics, and area, a cornerstone of geometry. It states that the entanglement entropy of a specific region on the boundary is precisely proportional to the minimal area surface in the bulk that caps off or ends on the edge of that boundary region.
Hold on, so if I'm understanding this, you're saying that the very geometry of space-time in the bulk is intrinsically connected to how much quantum entanglement exists between particles on the boundary.
That's exactly it.
That's truly mind-bending. It directly connects a pure quantum concept, entanglement, to a geometric one, area, in a calculable way.
It absolutely does. This insight suggests a radical new picture, that the geometry of space-time itself isn't merely a pre-existing stage upon which physics unfolds. Instead, it is encoded in, and perhaps built from, the intricate entanglement structure of the underlying quantum degrees of freedom on the boundary.
Built from entanglement.
This has even led to the highly speculative but incredibly influential ER-EPR conjecture by Maldacena and Susskind.
ER equals EPR.
Right. It suggests that maximally entangled quantum systems, often called EPR pairs, are connected in the bulk by a non-traversable wormhole, an Einstein-Rosen bridge, or ER.
Entanglement equals wormhole.
In a sense, yeah. It suggests that the very connectivity and fabric of space-time might be a direct manifestation of quantum entanglement between its most fundamental constituents. Severing these quantum connections, then, would literally be tantamount to tearing the fabric of space itself apart.
It's incredible to contemplate the universe possibly being woven from threads of entanglement, but let's bring it back to the current status of the AdS CFT correspondence.
Hmm.
You said it's still a conjecture, not a proven theorem, even after all these years. What's its current standing, and what are the key challenges?
You're right, it remains a conjecture, but it's one of the most robust and heavily supported conjectures in theoretical physics. We have massive amounts of evidence supporting it, including those spectacular successes where exact calculations in N for super Yang-Mills theory agree perfectly with predictions from string theory in AdS.
But challenges remain,
Significant key challenges limit its direct application to our universe. Most of the well-understood examples rely on very high degrees of supersymmetry,
which we don't see.
which, as far as we can tell, is not observed in nature. And maybe even more fundamentally, anti-de Sitter space has negative curvature, always pulling things inward. Our universe, however, has a positive cosmological constant. It's described by de Sitter space, which accounts for its observed accelerating expansion.
So wrong curvature sign.
Exactly. Generalizing holography to de Sitter space, trying to formulate a DSCFT correspondence, is an enormous and, frankly, elusive goal. De Sitter space lacks a clear boundary like AdS, and its symmetries are fundamentally different. Solving DSCFT would be monumental. It would offer a holographic description of our own expanding universe, maybe tackling cosmic inflation and dark energy, but it's really, really hard.
There are still other profound open questions that researchers are actively pursuing, aren't there? Like bulk reconstruction.
Yes, exactly. How do we precisely build local bulk operators' descriptions of points within the higher dimensional space solely from the data available on the boundary? It's like trying to reconstruct the inside of an object just by looking at its hologram. Very. And what about the mysterious nature of the black hole interior? How do we reconcile the smooth spacetime that an infalling observer would presumably experience with the boundary description, which seems to suggest something very different happens at the horizon?
Yeah, the firewall paradox and things like that.
Precisely. These questions are actively pushing the boundaries of what we understand about the holographic map, and they often involve deep connections to quantum information theory. Ultimately, perhaps the most profound legacy of this entire endeavor is the emergent universe paradigm shift it represents.
Space-time isn't fundamental.
Space-time is not fundamental but emergent. And that radial direction of AdS isn't just an extra dimension, it is the energy scale of the CFT. This suggests our intuitive notions of space and locality may be approximate concepts, appearing real and fundamental only because we operate at relatively low energies. They might merge from a more fundamental, perhaps non-local, non-geometric substrate of reality.
So if this turns out to be fully correct, or even just directionally correct, what does this all mean for the future of physics, for that quest for a unified theory?
Well, it means we are increasingly realizing the growing role of quantum information concepts like entanglement, information scrambling, computational complexity as potentially a new, maybe even post-geometric language for fundamental physics.
Beyond space and time.
Perhaps. The AdS CFT correspondence serves as our first and so far only truly concrete Rosetta Stone for translating between these two fundamental languages of nature, the language of gravity and geometry, and the language of quantum information.
And the future directions.
The future directions seem clear. Extending holography, if possible, to de Sitter space and cosmology to understand the very beginnings of our universe, cosmic inflation, the enigmatic nature of dark energy. These will be central to unraveling the deepest mysteries that remain. It's about finding the right language to ask the questions.
What an incredible deep dive. We started with this radical, almost fantastical idea that our entire universe might be a hologram, projected from a simpler, lower-dimensional boundary. We've seen how this powerful mathematical conjecture connects seemingly disparate fields. Gravity, quantum fields, the thermodynamics of black holes, even the baffling behavior of exotic materials like the Quark-Gluon plasma.
It ties so much together.
It really does. The correspondence fundamentally shifts our view from a universe built, on fundamental particles and forces to one potentially woven from pure information and entanglement.
And the profound power of holography lies in this incredible promise that by meticulously studying the quantum dance of particles on some distant, flatter boundary, we may ultimately unlock and understand the deepest secrets of the emergent, higher-dimensional gravitational universe within. It's a testament to the incredible interconnectedness of physics, revealing a profound unity where we once saw only separation and seemingly insurmountable barriers.
So, if our universe truly is a hologram, if space-time itself is an emergent property of quantum entanglement, what does that imply for the very nature of reality as you perceive it? Does it change your perception of the world around you? Keep that thought with you as you go about your day. Thanks for joining us on this truly mind-bending deep dive.